What role does the Laplace transform play in transfer functions? Imagine trying to understand how a complex electrical circuit responds when you turn it on or off. It can be tricky to analyze how signals change over time. That's where the Laplace transform comes into play. It acts like a magic tool that turns complicated time-based equations into simpler algebraic forms. This makes analyzing systems much easier. In electrical engineering, systems like filters, amplifiers, and control devices are often described by differential equations. These equations tell us how the system behaves over time, but solving them directly can be complicated. The Laplace transform takes these differential equations and converts them into algebraic equations by replacing derivatives with multiplication by a complex number called S. This process simplifies the math a lot. Once in the S domain, the relationship between the input and output signals can be written as a ratio. This ratio is called the transfer function. It shows how the system modifies signals at different frequencies. For example, it can tell us how much a filter reduces certain signals or how a control system responds to changes. The transfer function, often written as h of s, contains all the important information about system stability and response. The poles and zeros of the transfer function are key features. Poles are values of s where the transfer function becomes infinite, and zeros are where it becomes zero. These points tell us if the system is stable or not, and how it reacts over time. Engineers use this information to design systems that behave the way they want. Using the Laplace transform also helps engineers predict how a system will respond to sudden changes like a step input or an impulse. They can analyze transient responses and steady-state behavior without solving complex differential equations each time. It also makes it easier to design controllers that keep systems stable and performing well. In summary, the Laplace transform is the mathematical bridge that turns time-based system equations into a form that is easier to analyze and manipulate. It allows engineers to understand, design, and optimize systems by working in the frequency domain instead of the time domain. This transformation makes complex system behavior much clearer and more manageable.